This is video 2 for the electrostatics unit. In this one, we're going to begin by talking about conservation of electric charge. Now, we've talked about conservation laws before. We've had conservation of energy, we'd had conservation of momentum. Now we have conservation of charge. So for all systems, under all circumstances, energy, charge, linear momentum, and angular momentum are conserved. So again, we've talked about momentum and energy. Now we get to talk about charge. So for an isolated or a closed system, conserved quantities are constant. In an open system is one that exchanges any conserved quantity with its surroundings. So again, conservation laws only work inside closed systems. The boundary between a system and its environment is a decision made by the person considering the situation in order to simplify or assist in the analysis. So electric charge is conserved. The net charge of a system is equal to the sum of the charges of all the objects in the system. So an electric current is something we'll talk about in our next unit in greater detail. But an electric current then is a movement of charge through a conductor. And then a circuit is something we're going to talk about in great detail in the next unit, is a closed loop of electric current. So we'll talk about these A and B in more detail in our next unit. So let's consider this situation. I have a large spherical conductor with a charge of negative 10 coulombs. Next to it sits a small neutral spherical conductor. I then take a thin wire and I connect the two spheres. So what is going to happen to the charge? Will the charge on object A be greater than the charge on B? Will the two charges be equal? Or will the charge on A be less than the charge on B? Pause the video and take a second to think about it and make your best guess. All right, so if you selected this one, you are correct. Now, we can obviously see that this one right here is going to be wrong. I hope that you can see that one's pretty obvious. I imagine most people chose this one. You said, oh, the charge will be, electric charge is conserved, so I would have 5 coulombs move to charge B, or 5 coulombs would move to object B, 5 coulombs would stay on object A, and they would be conserved. They'd be the same. But in fact, it's actually the first one. The charge on A will be greater than the charge on B, and I can explain why. So first off, we have to realize that it's actually the surface charge density that is conserved. So we use, we typically use rho for density, so I'm going to use rho here. So surface charge density is going to be the charge per unit area. So that's how we're going to define surface charge density. So I would say that the surface charge density of object A must equal the surface charge density of object B. So I would say that the charge on A over the surface area of A must equal the charge on B over the surface area of B. If I cross multiply, I would get this expression right here. So notice then that if the area of object B is less than the area of object A, then object A must have more charge than object B. So hopefully you can see that, how that has to be true. So for charges, it does kind of matter. Um, a fun example of this: imagine that we have 10 people in a room, and one person, or 10 people in a room, and someone lets off like a stink bomb or something, and the people want to get away from that smell. They see that there's a small closet that's completely insulated from smell next to them. Well, if 10 people were fitting comfortably in room A and they try to go into closet B, not everyone can fit in closet B. So what'll end up happening is, instead of 5 people moving to closet B, maybe 1 or 2 would move to closet B to kind of distribute everything out while they're trying to get away from the smell. Okay, I mentioned earlier about electric forces, especially forces within a closed system. So electric forces result from the interactions of one object that has an electric charge with another object that has an electric charge. These electric forces dominate the properties of the object in our everyday experience. But the large number of particle interactions that occur make it more convenient to treat everyday forces in terms of non-fundamental forces called contact forces: normal forces, friction, tension. Um, so, for example, you are surrounded by electrons. All of your atoms are coated in electrons, which have a negative charge. Everything around you is coated in electrons, which have a negative charge. So when you touch something, the the negative charges on the electrons repel the negative charges on the electrons. So take comfort in the fact that you never truly touch anything. It's always the electric forces repelling that keep things separated. So when you are standing on the floor, you're actually levitating off of the floor because the electric forces are pushing you away. Electric forces hold atoms together. So if you have a rope, it's actually electric forces holding the atoms together that make up that rope. So it's the electric forces that keep the rope together. For friction, it's actually the electric forces between atoms in the two surfaces that cause that friction force. So electric forces kind of account for most of our interactions with everything we interact with in our normal environment. So electric forces may be attractive or repulsive depending upon charges involved. So remember, likes attract, likes repel, and unlike charges attract. So a force is an interaction between two objects. When we talk about electric forces, there must be at least two charged objects. Again, opposites attract, likes repel. Electric forces follow an inverse square law, just like gravity. So the electric forces are proportional to 1 over the distance that separates the two objects squared. It just so happens then that the way we calculate electric forces it's mathematically identical to the gravity equation. Remember, the gravity was capital G m1 m2 over r squared. Well, here it's k q1 q2 over r squared. Now I need this to be a vector, so I'm going to multiply it by the unit vector r hat. And then this gives me my equation for calculating electric forces. K is called Coulomb's constant, and it has a value of 9 billion. So let's use this to solve a problem. So let's consider that we have 3 point charges. Q1, Q2, and Q3 have charges of 6, -2, and 5 respectively. And I have them situated on a right triangle, a 3, 4, 5 right triangle. And I would like to calculate the net force acting on particle Q1. So the first thing I like to do is write the charges beside where they are. So Q1 is positive 6 coulombs, Q2 is -2 coulombs, and Q3 is positive 5. So if I were to look at the forces acting on this, I see that Q1 would be attracted to Q2. So I'd have a force here. And the nomenclature I would use would be 2 comma 1. So this is the force uh, provided by particle 2 acting on particle 1. Between Q1 and Q3, they're both positively charged, so they would be repelling each other. So those would be the two forces acting on this. Notice then that the net force then should be somewhere. So this would be like the net force acting on particle 1. It should be somewhere in the middle. So let's go ahead and calculate the magnitudes. So F2 comma 1, it's remember it's Coulomb's constant times charge 1 times charge 2 over r squared. So I would have 9 billion. Charge 2 is negative 2 coulombs. Charge 1 is 6 coulombs. The distance that separates them is 3 meters, which I would have to square. Notice I did not put negative 2 because really the negative just helps us figure out if the force is attractive or repelling. You don't have to put the negative in the equation up here. So for F2 comma 1, I get negative 1.688 times 10 to the 10th. Oh, I'm sorry, reading my notes wrong. There we go. So it's in the negative y hat direction because it's pointing down. And then F3 comma 1, 9 billion. 5 coulombs times 6 coulombs. The distance between those two is 4 meters squared. And this force is pointing in the negative x hat direction. So if I were to kind of put these back together, that means I would have a force of 1.688 newtons, or times 10 to the 10th. Then I'd have 1.2 times 10 to the 10th newtons pointing in this direction. Gives me a right triangle. So then I can find the angle and the net force acting on particle 1. So using the Pythagorean theorem and inverse tangent, I would get that this net force would be 2.07 times 10 to the 10th newtons, acting at an angle of 35.4 degrees, and then I'll just say it's south of west. So that would give me my force acting on particle 1. So there we have it. We have our electric forces. And it's just like any other forces that we do. You just have to resolve all the forces into their x and y components, and then just vector addition after that. Electric potential energy. Remember that the change in potential energy is equal to negative work, or work equals negative change in potential energy. Also remember that work is the integral of the force vector dotted with the displacement vector. So I can go ahead and start plugging some things in here. So the integral here. For the force vector, it's k q1 q2 over r squared, and it would be dr. Now the force is always, I'm going to say the force is always parallel to my R vector, my displacement vector, so I can get rid of the dot product that way. And I want to evaluate this vector from some initial position to some final position. So when I evaluate this, first off, you will learn in calculus that you always pull out all of your constants. So K, Q1, Q2 are constants. And I'm going to find the integral of 1 over r squared with respect to r. You'll remember in calculus that 1 over r squared is just simply the integral of 1 over r squared, or the integral of 1 over x squared, just simply 1 over x, so this is going to be 1 over r. So the work being done is going to be K, Q1, Q2, and since I'm going from an initial position to a final position, it's just going to be over delta R. So since work equals the negative change in potential energy, we see that the change in electric potential energy equals negative K, Q1, Q2 over delta R. So that is how we calculate potential energy. So a system with internal structure can have potential energy. So if I have multiple charges inside my system, there can be potential energy. Potential energy exists within a system if the objects within that system interact with conservative forces. So electric forces are now a conservative force. The work done by conservative forces is independent of the path taken. The work described is used for forces external to the system. Potential energy is used when forces are internal interactions between the parts of the system. So changes in the internal structure can result to changes in potential energy. So basically what that means is that we are now free to use conservation of energy, where we now have a brand new form of potential energy that we can take a look at. All right, that's going to conclude video 2.